Hello everyone and welcome to this lecture. In the last lecture we have seen some more bounds on algebraic connectivity in terms of minimum degree. Then we talked about the average degree of subgraph of a regular graph, and towards the end we have also seen the bound in terms of the expansion ratio. Expansion ratio was at most half of always greater or equal to the half of the algebraic connectivity. So in this lecture we will see some more now in terms of the largest degree, okay, and maybe some other terms also, and then we will talk about the relation between the algebraic connectivity of a bigger graph in terms of the algebraic connectivity of the some induced subgraph of it. Okay, so let us start with a relation between the maximum degree and algebraic connectivity of a graph. Okay, so let us start. Okay, so let G be a graph. Let G be a graph. In fact, a connected graph. Okay, connected graph. Okay, suppose there are n vertices. Okay, n vertices. The maximum degree is d. Suppose the maximum degree is let me call it by delta. Okay, maximum degree, and then there are suppose two subsets v1 and v2. Both are subset of vertex set of G. And one more thing is, suppose that this distance between v1 and v2 is greater than 1. Okay, now in that case then we will prove that. So let me go to next page. Let me write it here only. The minimum the algebraic connectivity is always less or equal to this maximum degree divided by this distance square as usual. Okay, and then times n divided by the size of those basically this vertex sets. Okay, vertex subsets. Okay, and then the number of edges which are which are not going here, maybe the number of edges which are other than the number of edges in G1 and G2. So again, G1 and G2 are the same graph here, so maybe I will. Okay, so let me write it clearly. Mod E G1 minus mod, so this is mod E G2. Okay, and these are G1 and G2 are nothing but induced subgraph on V1 and V2. Okay, so how to prove it? The proof is actually very simple here, very simple. Okay, so let us go to the proof of it. Proof. Okay, now we know that the distance here is more than 1, right? So suppose this is V1 here, this is V2. Okay, so this is V1, V2. Then definitely there are edges, right? So there is no basically you call none of the vertex here is adjacent to none of the vertex here. So situation will be something like this. So there will be the edges here, there will be edges, and there will be some intermediate vertices. Okay, so how many such vertices are there? How many such vertices? The vertices are here, n minus the vertices yeah. So vertices will be this, right? V1 minus V2, V1 minus V2. In fact, here actually I can actually write it more cleverly. In fact, more the better will be here. This V1 minus V2. Okay, very good. So sorry about that. So this will be the expression, correct expression. Okay, now what? Now what? If you see. Okay, let me write down the generalized expression. So u was always less or equal to 1 divided by degree v1 v2. Okay, square of this, then 1 v1 plus 1 mod v2, and then these edges, right? So the edges, so let me actually write this e g minus e g 1 again, and minus eg2. Okay, and then you take this. Okay, now if you see here, okay, so what about this number? what about this number? How many edges will be this? How many edges will be which are other than in edges in basically G1 or G2? Remember, the number of vertices here is n minus mod v1 minus v2, right? And the maximum degree of any vertex is delta, right? So the maximum possible number of edges that can be here is delta times this number. So this quantity is always greater or equal to, okay, so d v1 v2 is called the same thing, and let me write the same thing here, v1 mod v2, okay, and this is nothing but if you replace it by delta times this quantity n minus v1 minus v2, okay. So this will be the term, okay. Now the proof is very simple. Now the proof is this here in front of you now. So we can actually write delta here, okay. So this is delta d v1 v2 square, yeah, times, if you read this here, v1 plus v2 divided by mod v1 delta times, now delta I have already written, this is n minus mod v1 minus mod v2, this, now this quantity will be always lesser than n, right, lesser or equal to n. So actually now I can write this is nothing but delta d v1 v2 times n divided by, yeah, so this v1 and v need not to be actually basically they need not to cover all the vertices, okay. So n minus v1 v2, the only thing is they has to be this, right, okay, very good. So this we have proven, very simple, okay, very simple step, yeah, very good. So yeah, so that's all, okay, so it proves, very good. Now let us go to another result that is actually it tells the relation between or some inequality which relates the algebraic connectivity of a bigger graph or original graph with the algebraic connectivity of an induced subgraph, okay. So let us see it, okay. So let me write it first, let me first write it. So let again G be a connected graph, so let G be a connected graph, okay, and then again now here actually, so v1 v2 are subsets of your vertex SG, but now you assume that these are actually making the union of these two is actually whole vertex set, okay. Now suppose H is some subgraph, H is an induced subgraph, okay, and suppose the algebraic connectivity, suppose the algebraic connectivity and the algebraic connectivity of H is suppose mu dash, okay, mu dash, then what we can, so then we can write this statement then, okay. So the algebraic connectivity of original graph is which is we denote by mu, is always less or equal to mu dash plus the size of vertex set 2, okay. So H is induced subgraph on actually v1, okay, very good. So how to prove it? The proof is again very simple, okay, the proof, okay, very good. So yeah, so let x be an unit Fiedler vector corresponding to H, right, be an unit Fiedler vector, that means an eigenvector corresponding to mu dash, okay, unit Fiedler vector, okay. So Fiedler vector, okay, very good. And next what okay, so that means this. So suppose this is LH. Okay, so this is Laplacian matrix of this. That means if you multiply x with this, so this will be nothing but mu dash x. Very good. Okay, now what we can do is now let us augment x as follows. Augment means we have to increase the size of x by adding some entries. Let us augment x as follows. Okay, as follows. So what you do, x was this, right? So x was this vector. Suppose this was up to x. Okay, now here you add some zeros. Okay, so now suppose add here 0 0 0 such that the size becomes n cross 1. Remember, the size here was still the size of vertex at whatever the vertices in H were, right? And suppose you call it Z. Okay, suppose you call it Z. Okay, so this is augmented x. Okay, so Z is nothing but augmented x. Now you see that we know due to this Rayleigh quotient or what, this mu is always less or equal to Z transpose L Z. By the way, this this Z will also be a unit vector, right? Z is an unit vector, and also it is actually perpendicular to Z is also perpendicular to all one vector. The region is here, right? The region is given here because x is a unit Fuller vector, so x is actually here, so perpendicular to all one. So this Z will also be perpendicular to 1, and hence we can write. So this is mu is always less or equal to this, and which is nothing but, we have seen this again multiple of times, I over all edges. Okay, so this is nothing but Zi minus Zj. Okay, and the square of it. Okay, now the interesting thing that we have to see is this. Okay, so these are two, so basically vertex sets here, v1 and v2. This is actually nothing but H, right? Subgraph H. Okay, and then there are the edges. Okay, now if what so what about, so let us actually see the terms here. Now break the sum into three parts. So for any edge I and j, okay, let's just consider these three cases. Okay, all the three category for edges where both endpoints are in v1. Okay, second is one endpoint is in v1 and none of the endpoints are in v1. Okay, the third is none of the both the endpoints, none of the end points are in v1. Okay, so here it is also v1, sorry, in v1. Okay, now if you see that if none of the endpoints are in v1, okay, in that case this vector will be what, this quantity, because z was this, right, x, right, and then 0 0 0. Okay, so this is actually corresponding to v2 if you see carefully here. Okay, so now this is corresponding to v1, so this term will be giving 0 contribution, so 0, so this is 0 contribution to this, right, 0 contribution. Okay, yeah, okay, and what will be the contribution from 1? Okay, contribution from 1 will be what, if you see here, if the both edges are in v1, that means both edges are in H. Okay, and if you are talking about this, if suppose this is H and both endpoints are, this is nothing but, in that case is nothing but this x transpose L of H times x, which will be nothing but mu dash, right? This will be giving you this a kind of mu dash. Okay, very good. And what is the contribution from this? Okay, one endpoint in v1. Okay, so basically, and another point is in this, so that part will be 0. So only that Zi will be surviving, which will be in fact equal to 1 only when this. Okay, so let me actually see this. So how many times this term will be surviving? Yeah, so this term will be surviving the at most the number of edges here, right? This at most the number. So how many edges could be there? There can be at most the number of vertices in v2. So we can now easily write this. So this quantity So mu is nothing but mu is always less or equal to contribution from this plus contribution of this. So contribution from here, it is nothing but mu dash plus the number of, at most the number of vertices here, right? V2. Okay, so this proves the theorem. So no need to confuse here. Okay, so here the number of edges will be at most this, and you can now see the entries. So this the entries will also follow this, and at most this mod v times the this quantity will be at most mod v times. Okay, very good. So this proves this very cute and very useful this inequality. Okay, so with this I am stopping this lecture. Thank you very much and see you in the next lecture. Yeah.